So I've seen last time it's already.
So, so let us start. So yeah, so today I can continue with my talk. Now, to remind you, basically the main theory which proof I explained is the point to one given. So in AC proofs that is delayed. Where D is a recursive pair. Then D is embeddable in the lambda x with omega to x plus 1, omega n, but plus 1, that is, we have the style of mixed sensation of the height. And for some stuff. And right, so basically this the main but this five. And really, okay, this of course is a variant of orbital analysis. In this case, of course, we do, but in this case, so the main difference is this kind of, say, standard orbital analysis of P, where we prove that if, say, A or AC0 prove that something is well ordered, then its order type is less than epsilon, or in other terms, it's if the something order that this order is embeddable into omega or some. So this is the main difference between this classical result and what we are doing is that essentially we need a much higher degree of uniformity of analysis. So since really we are here talking about embeddability of the lattice, so the lattice are, to remind everyone, the lattice are this kind of relativized ordinal notation systems. So where you have system of terms, and then when you apply the later to particular linear order, you obtain an order as an order on terms, where you substitute elements of your input order inside of your terms. Right, and yeah, so basically it's a kind of this relativized system. And here, when we talk about this embeddability, it kind of means, so okay, from other perspective, let's particular kinds of category of well orders in itself. And yeah, and basically here we're talking about in terms of this natural transactions. In other words, really we want additional uniformity conditions on this bounds that we are obtaining from ordinals. And that's really the main thing. Yeah. Okay, so I think so. Last time, basically, I explained, I think, kind of basically this grand scheme of how the proofs. So something along this line. So we okay, so just you throw that if the AC is correct. So this was equivalent to AC here plus additional so that some that x is below, where x is the additional set constant. This proves that as is very for statements something later. Right, so, mm, so basically what's happening here is not nothing else than simply introduction of new kind of fresh constant symbol. So basically we can deal with the universal modification introducing new constant symbol, and then we apply deduction. So that's really as elementary as it gets. Right. So next equivalent is okay. So also no. Particularly that is if you can go to this setting of first order series from second order. Now we're dealing with theory A of X. This A of device to fresh memory predicate symbol SN. And we have theorem of X transfinder. In other words, okay, basically we're treating this one X as a code for linear, and we're asserting that we can transfind. So, and the theory is proving that if y is aggressive in the set in the linear order G of x, then G of x is containing y or another. Yeah. So basically, the matrix of this Lorentz assumption, and we simply can drop one universal quantity. And then, okay, and then really what's happening here is essentially the same thing as the usual conservativity of PA so over AC0 over PA. Or strength formals. Okay, so this again very easy. Okay, so next equivalence is I think slightly more substantive. Basically, you can go from this theory K. So essentially, okay, this constant X is it really was a constant over linear orders. That's X is a linear order. But for technical reasons, it's not good enough. We want not a theory that can talk about linear orders coded on natural numbers, but rather we want a theory that talks about abstract, and it's completely abstract linear. And okay, I guess I explained a bit like why precisely the this button also next use the top. So then we could go to the theory KPU. Let's see, KPU over. And so what is this theory? So basically, to remind everyone, so TPU is of course a theory, set theory that allows us to talk about Ure. And basic idea is that Ure elements that form some kind of. In this case, basically, we want this underlying structure to be a structure of linear. Here, this check. So this O is this class of your elements, really, and we're thinking that it's kind of linearly ordered elements. So it's coming with the signs in the order. Okay, and then basically now O replaces X, right? So because X before was this abstract linear order, and then we're getting a principle of O transfinite reduction. This conclusion, of course, of simple density of D of O. Y with D of O implies that D of O subset of one. Okay, again, so I think I commented it last time on this, but basically the kind of the proof of this equivalence is via forcing. So I mean, this is not again nothing too fancy for people familiar with forcing style arguments. You basically okay. So what is the difference here, right, between these two theories? Kind of both theories really talking about some abstract linear order or abstract well order, and kind of the But the difference is that the kind of theory on the bottom treated as a completely abstract thing, and theory on the top treated as a sum, as a linear order of natural numbers. And yeah, and so the way, so basically the way how you, okay, of course, non-trivial thing is to show that if something provable here, it's also provable here, as direction is trivial, because this theory clearly has additional information about this abstract linear. Yeah, and but basically then we simply collapse class of your element on the class. We do Levi collapse of class of your elements onto the class of natural numbers. Actually, yes, I think I forgot to mention that TPU is actually a very big theory, and again, basically doesn't contain axiom of infinity. So really here we're talking about entirely defined sets. Yeah. So anyway, so basically you can just kind of making or class of your elements countable variables. And that's it. Okay. Mm. Okay, so so at this point we kind of ready to employ kind of infinity proofs, and this is really is the part on which I want to focus today. The test. So what you want to say that okay, there's two things. First of all, basically, if we so okay, now if you have so height was we have just made this equivalent statements, but now we kind of start to lose some information. So we oh, okay, if we do it not insufficiently uniform, right? Yeah. So we say that if so this kind of this theory KPU plus KPU O plus is transparent cache principle proves something is that in fact for every alchemist block um, we you have a proof of the rank yeah um, for every alchemy and you have this thing we prove that yeah, so basically you prove the regressivity your progressivity of y implies yield or being something like that. The prevail, basically what this means is that kind of here it's so this is for the statement of probability in infinity logic, and namely this is probability in infinity logic for a kind of canonically corresponds to the structure HF of outcome. Full structure. And of course, the structure of hereditary finite sets, where your elements are, yeah, basically where your elements are ordinal smaller than alpha. So here, of course, you can, yeah, right. So basically, the kind of ordinal not in the set. So basically, we don't in the structure we don't treat ordinals as set theoretic objects. So basically, they're your elements. So it's sounds obviously that two kind of ordinals, the kind of natural number that live inside of HF of alpha, and that's kind of before that are one Neumann ordinals in terms of the structure, and this ordinal smalls are not came from outside, and they are just pure elements. Anyway, but okay, but anyway, this kind of we have this notion of infinity, kind of completely mimicking the notion of omega logic. in the most straightforward way, right? Because what is HFO? Some sort of infinite structure. And yeah. Mm, yeah. And then we have this the counterpart of omega rule, that is HF of alpha, where you, in order to conclude that universally quantified statement holds, or to have this rule where our conclusion is universally quantified statement, we use all instantiations of this universally quantified statement as our premises. And this is HF of alpha rule. Yeah, anyway, so this is actually explained this in more details last time, but I guess I don't know if do people want to be reminded about the rules of HF of alpha logic? Perhaps no. Anyway, basically, but again, so it's just if
They're on YouTube if people want.
yeah, I don't know, but they could look on YouTube. They could simply go back to the previous step.
Yeah, exactly.
Yeah, so right, but basically, there's nothing complex about this. So that this is just indeed direct analog of omega log. All right. What I actually haven't talked about in any details last time was that we need slightly more uniformity than I wrote right now. We want to say that basically we want to say that okay, this family of proofs that we are getting, this family of infinity proofs we are getting is in fact is kind of behave in kind of in a nice uniform way with respect to all. Or okay, so basically what okay now we need to know this HF second HF alpha. So F alpha ranked by Dalton or anyway. It's a set. Uh, Derivability acceptance. Uh, which the form so rho gamma. So where gamma is HF of alpha sigma, set of final set of alpha sentences. Which basically means that we just sentences is a language of KPU of with additional predicates. Where we actually can use constant from HFO. Okay, and so gamma is fine. So rho is simply a natural number. Okay. And finally, beta is an element of f of alpha, right? So this is basically why this is called HF of f rank, basically because we rank. So our ranks they're supplied by radialator f. And of course, the condition is that if something is in the proof, it should be kind of derived by some rules. So such that for any certain small from the capital, there exists a rule by which it was derived, such that all its premises are inside of the capital. a rule f run f of alpha run it just alpha. So we have some premises I for I of from right. The conclusion is so rich. Whatever I from I, P I is from anyway, basically we can deriving P by this P by some sort of rule that is such that all premises are within P capital. Anyway, the kind of national. But it was kind of important to formulate these proofs as of durability because now what we are saying now is that a vector proof is a finite functor from ordinals to the category of sets, such that it's such that pointwise it consists of proofs. Um, and vector proof. Subset normal finitely. Let's say F. About that, from from category of linear orders to the category of sets. Such that the pointwise consists of the elements, I guess, say, for example, ordinals just equivalent. You can always extend from ordinal to all sets. Such that pointwise each is an right. But I can't really explain what I think this. Okay, I think actually I probably want to explain a bit what finitely functor means last time. Basically, finitely functor means that you, yeah. So basically, when you apply, I mean, okay, there is a formula. So basically, the idea is that the value of finitely functor on infinite structures should be simply union of the values of the functor over all finite substructs. This is basically what it boils down to. And subset normal simply means that basically it maps set theoretic conclusions into set theoretic conclusions. So actually, I think actually that's actually the same amicable from category of linear orders. Yeah. So subset normal means so basically if for it means that if you have two linear orders, that one is subset of another. P of A is subset of Q. this is, the image of the identity map from A to B is the identity. Okay, so basically this is what a bit uh, yeah, in other words, we have sufficiently uniform families of infinity replaces. Um, um, uh, now the kind of an important claim here is that in fact here getting an infinity proof. So we are getting a bit proof and not just kind of 0.5. So in fact, so we have a bit proof. So in fact we have yeah. There exists the bit proof such that this particular sequence will be an element of P of alpha. So where is a time. So they makes sense. And this P, and you could say that, like, say, P is omega n plus 1 lambda x, omega n plus 1, x plus 1, rank 2. And this is kind of kind of first thing that we need to achieve. We kind of want to get kind of. So basically, of course, what happened here was okay. For people familiar with ordinal analysis of P, it's basically was just direct counterpart of the embedding lemma. But now the point, of course, we made embedding kind of. Yeah. So you kind of what we are showing is that really this standard embedding lemma could be made factorial. Right. Yes, we can do it, but right. So okay, so what is the next step? And of course, typically, kind of the way how you kind of to achieve, or you normally to achieve ordinal analysis. From this, we need two more steps. Namely, first we need to do cut elimination, and secondly, we need to have bounding sum. So this works like this. So okay, so we have this. Then we actually can do cut elimination. Then there exists a proof P prime. So it exists n prime and p prime. That is p is lambda x omega n prime plus 1 rank. Such that for every alpha, p of is a proof of basically. And that's basically kind of going from this some non-cut rank to proof with rank 0. And of course, the proof does. So in fact, so anyway, this is basically here. What we need to do, we simply need to kind of have a variant of cut elimination that works for punctuations. Just, yeah. And finally, so I think in some sense, kind of more interesting part of what going on here is what's happening. That is what's happening with boundness. And the point is that for boundness, okay, so okay, so basically, if you kind of inspect the standard proof of, okay, just so maybe I'll remind everyone what is boundness lemma. So boundness lemma is a statement that if you basically prove this kind of conclusion, this if you the boundness this so we could say talking for the case talking about the case of generalized. So if we have say alpha zero probability of the that some order less than prefix, so if basically progressivity of some set along linear order less than implies that um, so y contains the whole domain of the order. Where
Can you move the camera?
Oh, sorry.
Okay, if less than it's recursive. Sorry. Recursive linear order. Then for type of less than is bounded by up. Yeah. Yeah, I think actually if you put it like this, probably would be small enough because you have to the stop most complications that you use. So basically, you kind of important point here is that okay, if you kind of do the standard, and of course you can prove exactly the same result for this HF of alpha logic. That's not a problem at all. If you simply want to make a bound with order types, you can simply take standard proofs from the literature of this very classical lemma, and it simply will work. So, okay, this very minor adjustments. Since we're taking a slightly different field, there's no substantial difference. However, the few problems is what we are doing here. So it's basically the problem is that this result is really not sufficiently uniform at all. If you can put it like in this form, so then we simply say that we have a bound of the type. Since I mean, so basically the problem is that the later they do not behave like ordinals in the sense that you don't really have this global linear order on the latest. So you the kind of they do have considerably more complex internal structure, and you really have to talk. If I have to talk about compatibilities of the latest rather than simply this kind of order type bounds. Okay, technically. Yeah, technically, there is an easy version of the result, which will be delivered by basically what I just talking about this not kind of application of standard bounds. So these versions where instead of stating we have an embedding here, we say that we have pointwise bounds, right? We say that for particular when we have particular alpha, then like basically for each particular alpha, d of alpha is bounded by this. This will be a much easier result, of course. And actually, you don't wouldn't even need the steps that I outlined so far. You see, I basically would simply use very standard techniques to achieve this. Yeah. But so, basically, what I'm saying is that here we want to achieve so extract more information from presence of this AC0 proof of something being delayed. And okay, and for this we need kind of final version of bound slide. Okay, but not that. Okay, so kind of going back to the bound. Okay, typically the way how to prove boundless number is via transfinite transfinite induction on ranks. And this is usually in this proof, I can say, extraction of information from infinity proofs. Okay, so basically you kind of so what you do, you kind of somewhat generalize the actually kind of I don't have it in my head in very old. The idea is the following. So you slightly generalize this assertion so that okay, you kind of put in things as statements of approximately this form that has some side concept gamma, then you have okay, not progressivity, um, and then you can put in the situation and this applies that A is an um, 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 okay, I just kind of unravel with in order with this connectives. And then you have certain condition of what gamma, side context gamma can be. And then basically, okay, then okay, you can switch like and you have some sort of successful proof of this. And then what you're proving is under this kind of condition, you could say that there is some bound on what is the position of A in the order lesson. Kind of roughly it's order. But as now I can forgot very precise details about this, kind of what was the inductive assumption here, but it's basically because of this. And okay, and then if you kind of inspect what kind of information you really can extract from this, is that you in fact can extract a simulation. That is, you kind of think about okay, basically what we want to kind of have this we want to obtain something, say, more constructive than simply order type up. So you want, okay, basically, optimally we would want to have an M, but again, for explain we can get away with a bit less than an M. Namely, what we it's kind of relatively easy to extract are simulations. And this could be extracted in a completely computable way. So in some, so essentially, what you can you could kind of see that your the complete proof contains this sort of durability assertion. Essentially, you could say that this kind of durability assertion is this tells us that Bitcoin is a candidate for a point where A can be embedded. Right? We want to embed this order less than and order alpha. And basically, when we see this thing, we say that okay, so here we have this order less than, and okay. Okay, and at some point we have this A, and here we have that. And what we are saying is that okay, when we see this, basically we say that Bitcoin is a candidate for the point where A can be embedded. Again, technically it's slightly more complex because it's because of how actually induction works. but roughly it's what's going on here. And so, and what does it mean to be a candidate of a ticket? Actually, it means something quite precise. It is so basically, since of course this A can appear in multiple sequences, right? So you kind of it's possible that you kind of prove this thing with for one bit, and then you prove it for some bit prime, and so on. So you could have actually multiple kind of candidates where A cannot be applied. But if you kind of observe that there is kind of some candidate point, then whenever you can consider some smaller b, say smaller a prime, they will be smaller b prime, saying that kind of beta prime will be a candidate for the place where a prime should be embedded. Yeah, basically this is kind of essentially play this condition for what it means to be a simulation. So it's kind of so this is right. So right? So let's say for every a and alpha, or if so if a is simulated by alpha, then for every a prime, so if a is less than a, there exists let's say um, there exists beta prime smaller than beta such a prime is simulated by beta. So, okay, and the point is that in fact this simulation relation can be made simply recursive. Well, basically, as long recursive in the since we're really extracting the asserting the something is simulated, that the sequence itself is our sorry, it's recursive, so it's recursive enumerable, not recursive. You can losing some amount of information. Yeah. Right. Now the point. Okay, the point is kind of this version happened to be more suitable for this dealing with functorial with bit because kind of a bit counterpart of this is that when you have a bit of this kind of fashion, then you can instruct a kind of a family of simulation that will be a finitely functor itself. So then this implies that there exists that is fun from okay, linear orders to categories. This is just basically it's maps linear orders to the respective simulations. Right? So, so every so that's is finally it's etc. Finally, for every a, S of a is a simulation of G of a. Yeah. And double prime G of a in omega double is in double prime for a plus. Okay, technically, I think of course I keep a bit of details here. So I think like this usual boundness lemma is if you have particular rank on the proof, kind of the rank here will be slightly bigger, but not by much. It's basically the reason how this simulation is being built. Actually, it's, being more precise, I think it wasn't simulation alpha itself, it was simulation omega times alpha. It's not a big difference, but a bit of adjustment for technical reasons. But anyway, the point is this kind of expressions of these omega expressions, they can absorb in itself a kind of slight manipulations with ordinals, so it doesn't. And okay, and this will be maybe this functorial simulation. So we will be this kind of functorial family of simulations. And now the point is that when we have this via certain trick, we can improve this functorial family of simulation to an actual embedding. So we do this one. So, back when I was explaining simulations to you, like you thought that it was completely stupid thing to do to begin with, basically because I mean, of course, like simulations are certainly useful too with people dealing with things like model logics, like Kripke frames and so on. But here we're really talking about linear orders, like simulations, and actually even in the typically linear or really linear orders we're talking about they're really even well. And for well orders, actually, it's when you have a simulation, it's extremely trivial to extract an embedding. That is, you simply do pointwise minimization. Right? So if you have a simulation, then it's kind of pointwise minimization is an embedding. If you kind of put each A, you keep the least possible candidate where A should be embedded, this will have to be actual embedding. This way, very trivial to check. Yeah. US is an actual embedding less than in output. This is nice, but a bit of a is that if you do that okay, so naive approach would be to do this pointwise here, right? You simply do pointwise, but the problem is that this doesn't work because what you get, unfortunately, it will not be a natural transformation. Right? So basically, okay, you can do this pointwise minimizations, but because kind of okay, what's happening, right? So in each kind of when you're going from smaller order to bigger order, the big order has more elements, and when you're having more elements, you can kind of basically more simulations can happen, and hence basically you do not necessarily have this agreement, right? So basically, this when you're switching from smaller order to bigger order, like even if some element was already element in D of small order, the place where it should be embedded according to simulation was the same. It might be actually bigger than the element where it will be embedded according to minimization of simulation for some larger order B. Is this kind of anyway? It's kind of you kind of break it. Basically, you can break uniformity. And okay, this is a bit of but in fact, there is a fix to this. That is, you kind of basically you can if you kind of so basically you need to do minimization in a slightly larger order, and this solves the problem with uniform. So namely, okay, So, mm, 11. So if S basically S there, so um, mm, is the normal infinity family of symbols. So A is a simulation of some data. U of A in a data f of A. So the value of data f of A. So if this happens, then you have the following network transformation from D to X. Namely, say, so then F small. So, so we want to define a natural transformation of A to in fact not of A, but rather to f of omega plus omega A. Uh, F A of A of some E J1 J equal to mu S of omega A of omega plus omega A1 or omega plus omega A2. So is a just A is a linear is a initial transformation. Transformation from D to lambda x f of omega plus omega x. Okay, so what's good? Yeah, I mean, this is okay. I think maybe what else was we can slightly about, but basically, okay. So explaining this was the problem that when we do this minimization of simulations, kind of to construct embeddings, this kind of values could change when you go to slightly to larger orders. And here the idea is really to take these values for the following large order when we go from order A to order omega plus omega times A. That is the kind of basically in all the gaps. So basically you have order A, and of course you have this gaps between elements. Essentially the idea here is that we're adding a copy of omega in all the gaps. This is basically what omega plus omega times A is doing. It's a kind of this having this, adding this infinitely large gaps between elements of A. And if we do minimization in this order, then this basically is as good as any other order. So it's kind of, if we do minimization here, this minimization actually agrees with minimization in even large extensions. This is kind of the point. And so why this happens? This basically happens because function f, this kind of function s, happened to be finite. That is kind of only really is kind of values on kind of arbitrary large objects is they determined from values on finite subobjects. And that is okay. I think I will not really be going into very deep details of this proof, but I mean, essentially, it's not very hard proof if you know that kind of, especially when you know the answer. Yeah. Yeah, no, but so basically, the point is that when you kind of doing this omega, going from A to omega plus omega times A, so saying basically adding this infinitely many elements in all the caps. And what this particular entails that if you have any kind of extension of A by finitely many elements, then this extension could be kind of mapped into this order where while we kind of keep elements of A on their places, right? And if you think about this order as A and found by some additional elements in the gaps, then basically you can do this. You kind of put whenever you have any finite extension of A, you could map it here. And this is basically the reason why it works. It's kind of, this order is sufficiently large to be universal among all possible finite extensions. And since our simulation was a finite factor, it kind of produce some sort of weaknesses for this for any kind of extension, even kind of extension by area, infinitely many elements. This is already witnessed on some finite extension. And hence it's kind of enough to deal with finite extension, and it happens to be enough to transform. And okay, so that's a couple of additional tricks here for it to actually work, but basically this is just okay. Right, so this is and this is basically how we extract this symbol. So okay, so I think the part that I haven't yet really explained was this part about how we actually deal with this bit proofs. How I mean, say I was telling you, okay, so basically we are getting this bit proofs, but why? So, I mean, yes, there's a few ways how you do it. And then actually, I mean, this I guess is not again. If you simply want to achieve the results, then I don't think there are any kind of fundamental problems here. Yes, you simply can yeah, basically you can do it by in the end you kind of can do it by hand, just dealing with this kind of functors and showing that yes, indeed, when you do these manipulations, everything goes well. But in fact, so okay, so it's kind of it wasn't necessary for this particular proof, but even as in kind of in the same paper that we are currently writing this one, so we have a second theorem. It's a bit stronger, so it's about generalization of this result to real kind of relativization of AC0 by axioms that something else is a delay. And already to kind of prove this theorem, we need to have the previous results to be formalizable inside of AC0 itself. And basically, what this entails, we actually have to deal, kind of be able to deal with these functorial proofs in sufficiently effective way. And in fact, and the point is that we actually what we can deal with are simply recursively enumerable bit proofs. And so, what does precisely this mean? Okay, I mean, if you first of all, if you look at stability on natural numbers, this is quite basic. That is because this proves that their values on orders are reconstructible from the values on just finite orders. And because it's like you simply need to know the values of the functors on natural numbers. That is really you can reconstruct the value of factorial simply from is kind of countably many vectors. So proof of zero, proof of one, proof of two, proof of all. You just take single value of proof of omega in which you could reconstruct also once. No, actually, sorry, this is actually wrong assertion. If you simply take proof of omega, that contains slightly less information. Yeah. So you need the values of p of zero, p of one, and so on. Yeah, but then of course you can simply say that one way of dealing with defining what an array proof is, you simply say that all this kind of if you consider this family of individual values, then it can in totality it could be coded by an RE set. Or no, it's uniformly RE. It's one way of saying this, but actually, what happened to be a bit more productive way of stating the same thing would be to consider relativized stability. That is, yes, kind of we will be talking about ability, sigma definability in the structures HF of A, and so in fact, we have the following result. Um, um, for family values, family of HF A P of A. The following I have. P um, E is a recap. E is an RE dictable. Okay, here I kind of skipping this part about trunk, right? So basically, it's, I assume that it's trunk by we have fix the like F and we are talking about F trunk with rules. And these values are uniformly sigma definable in structures HF of A. Is uniformly sigma definable in and so basically what this okay, so you kind of simply looking at the individual structures for HF of A. Of course, in structures for HF of A, you really can talk about it's kind of as usual with the business of 50 plus the Platex theory with Euro, so you really could think about of admissible sets with Euro, and of course HF of A are admissible sets. As this kind of just where you have a general you have some sort of internal computability theory. Anyway, the point is basically inside of the structures you really can't code notion of derivability assertion, because I mean, what's derivability assertion? Basically, it's formula that uses this hereditary functions as constants, and just otherwise it's simply some just finite expression. Okay, relativized to particular order. And okay, so you can simply could talk about the derivability assertion inside of HF of A. And then hence you, when you kind of talking about some of the durability assertions, then they can be definable within HF of A. Um, okay, and here we're talking about uniform sigma differentiability, which means that you have a single parameter-free sigma form, and it should be defined, and for all the A's, it should be defined into a Q of A. It's a kind of, you can basically have this uniform definition of the thing. And curiously enough, this actually, if you don't here, you don't need to put any extra conditions that this somehow you demand that this value should be functorial, as a kind of should kind of agree with each other. You don't. Basically, simply the fact that the sigma definable, kind of uniform sigma definable, you can kind of prove that in fact they do form edit the proof. The point is that simply when you're kind of considering this computability with your elements in the structure HFA, I mean, structure HFA, it really couldn't distinguish between different elements of linear order in effective way. And because of this, really, when something is computable, in the structures, it's kind of computable in a way that wouldn't rely on some kind of accidental sense. And hence it have to be sufficiently. Again, of course, it's not a problem. For proof, we actually need to prove it. Again, it's not very hard, but it requires some time to verify. Okay, and so basically the point inside here, of course, is that really instead of talking about, so we can simply skip all the business of verifying that things indeed are. And we simply can, as long as we can guarantee that our operation, our transformation flow, they are kind of are within the structure. So basically, as long as you can do all your manipulations, proofs, and talk, kind of has enumerable tool inside of the structures HFOM, you're good, because then you're simply guaranteed that you will be able then to extract basically the proof will be agreeing with each other, and you will be able to in totality they will form a big total. Okay, this is kind of inside one here. So this, yeah, and then okay, there are kind of two ways how one can deal with the rest of them. So what? So basically, there is a kind of one fairly explicit way of doing this. Basically, we are kind of it would be to kind of talk about positive sigma operators on array proofs. And so basically, I mean, so what is positive sigma operator? It's kind of very easy. So you kind of have essentially have array set. Oh, yeah, it's technically don't have to assume that it's array, but typically you could think it's an array. And then you're producing another E set in a way that kind of depends on your input array set in a positive way, right? So kind of the bigger the input set, the bigger the output. And the definition itself could be kind of sigma definition, and then you can guarantee to map sigma definable sets to sigma definable. So, yeah, and so basically now we want to really talk about the sigma manipulation with infinity proofs in terms of the positive sigma operators. And okay, but one have to mimic the standard proof of cut eliminations. Oh yeah, actually two things. Basically, the word was lemma, that was technically the hard part is cat elimination theory. So let me focus on that. And so, and okay, so now we kind of want to perform this cat elimination in terms of this positive sigma operators. And in fact, you can simply mimic the usual proof of cat elimination theory as long as you have right notion. And the right notion happens to be not strongly proof-preserving operator. So it's not and basically strongly proof-preserving operator kind of this. So basically, we not simply want our operators to mark proofs of course, but we want our operators to have this property that if you kind of have this one-step proof address, if you have like your operator, you have your proof operator, and then let's say H. And so it's kind of, and then you say you apply it to some P, where P is actually not a proof, but
No, sorry, I just forgot to rotate the camera.
okay.
So, yeah.
But is kind of just it could be the kind of a segment of so such that basically to say in the yeah, okay, so basically we have situation, so we have P, so the format we have P, and then we have smaller thing prime. And then the properties we want is that all heritability assertions from T they are justified within P, right? So kind of if you have some heritability assertion in T prime, then it's derived by some rule such that all premises are within P. And then basically what you want is that H to transform this kind of one-step proof frequency into one-step proof frequency. Okay. Transform basically should go. Okay, basically basically конечно, we can pick the pair here. The prime was as I just explained. So that whenever you for every derivative within P prime, it's justified within P. Then this pair H of P prime H of P should be having exactly the same property. And this is kind of a stronger property than just proof preservation. So essentially, you're saying that kind of when you have kind of one-step justification, you could make one-step justification the conclusion using one-step justification the premise. Something. One-step justification in the image by using one-step justification in the brain. Yeah, and okay, anyway, the point is that if you kind of this kind of notion happens to be correct, notion which allows you to actually mimic the standard notion. So then when you're kind of dealing with this strongly proof preserving code, then you simply first proof say in inversion lemma, then you prove reduction lemma, and finally proof tap elimination. And all of them are formulated in terms of this operator. So essentially, you have operator performing inversion, you have operator performing reductions, and you have operator performing cut elimination. Yeah. And I think one caveat here is that you need to slightly modify the calculus. That is, you have to allow to have repetition rules. Okay, anyway, that's a bunch of techniques. I think and in fact, the fact that you need to do this weakening of the calculus repetition rule is certainly not new. I think this kind of this observation, so that when trying to deal with this with infinity proofs in a recursive way, you have to extend the calculus repetition rule is going back at least to kind of paper Grigori Mintz from like early 70s, I believe. So it's quite old observation. And the second, but conceptually, is actually in some sense, I was just saying that this kind of, in some sense it is, but in some other sense it's not really the same proof. It's kind of, you have kind of the same steps, but as a way how you kind of prove kind of individual laws, it's actually a different way. Because usually when you're dealing with this proof, the way how you prove indeed kind of individual laws about proof kind of manipulation is via transparent induction. Basically kind of proving that okay, if some property you can prove some property for all derivations of after rank, and then you can go to next rank. This is basically how it usually works. But this is not what's happening here. So so this is basically the start could be and what's happening here is more like coin tactic. So you really more think about these proofs as kind of you can just looking at the top basically what's happening in the top of the proof, and then the way how you build up your result of proof is by pushing justification up. So you kind of basically you kind of the way how kind of this inductive proof works is that you simply should be able to guarantee that you could delay giving justification indefinitely for definitely long time. And it's really somewhat different. And if you kind of look at the exact converters, it's somewhat different group. And this is what was mentioned. This actually doesn't work for the standard variant of the calculus or the variant of the calculus with the repetition rule. So there are some combinatorial differences actually with regard how to prove. Yeah, okay, anyway, this is kind of basically one of point. Anyway, but then indeed, so if you kind of switch to this language of positive signal operators, then you kind of could do something at least very similar to the standard proof. And then they can do it pointwise and things just work. That's automatic way of starting with yeah, so kind of this is a bit kind of actually I haven't checked this other thing that I'm going to say. That carefully, but actually now I'm kind of looking at kind of different way of doing the same thing. That is there is this there's a paper of Google about conservativity of theories of intuitionistic theories of fixed point of strongly positive operators. Anyway, that's kind of the point is that strongly positive. I mean, of course, this kind of probability notion, infinity probability notion, they happen to be fixed points of certain kind of operator, of certain kind of monotone operators. Okay, basically, you simply say that this kind of the resulting set of kind of derivable things is closed under the rules of the calculus. But what happened to be the case that actually the corresponding operator for which you construct is strongly positive. Yeah, well, I think I want to wrap this up very soon, so I will be explaining what besides strongly positive is, but it's certain kind of syntactic restriction. And so really, you kind of when you're dealing with this infinite triples, you kind of you're dealing with the strongly with this fixed point of strongly positive one. And what happened to be the case is that when you okay, so okay, it's kind of going making step back and instead talking about like this case of TPU, we're talking about standard arithmetic case, this usual omega proof. That okay, what's happening is that if you kind of if you want instead of kind of if you want to formalize things in intuitionist contacted temples, you can take alternative semantics. And practically, you could take realizability semantics of intuitionist charisma. And realizability semantics basically is kind of this instantiation of BHK interpretation. That is, if you essentially witness for something to hold is computational witness. You can actually, if you something exists that you, it means that you provide it in this way. And okay, and then you instantiate this in terms of programs. Basically, what realizability semantics is. And then, really, in reality, you can extend realizability semantics to to this two maximum fixed points, but they not be maximum fixed points in the real world, but they will be maximum fixed point from perspective of realizability semantics. So the kind of basically fixed point will be simply union of all recursively enumerable prefix points. Again, it's kind of externally this doesn't work. This is not a real fixed point, but because from perspective semantic everything is computable, being and we put this additional restriction of operators being strongly positive, this kind of having simply taking this union of RE fixed points happen to be enough internally for this kind of doing living inside of realizability semantics. In fact, you actually, okay, this is what's happening for the case of, oh, but then you can do the same thing here. So you can version of reliability semantics for KPU, and then you could have this analogous theorem. And then, yeah, and then what you can show is that in fact, when you prove that inside of the kind of improve the inside of reliability semantics that something is infinitely provable, then you can extract a computably enumerable infinity, or more precisely, since we're talking about this KPU case, we're talking about this, we'll be able to start with this uniform sigma definable things. And yeah, and so basically, and in reality, what you're getting is the theory of maximal fixed points, and where you actually can naturally reason in co-inductive way. And yeah, and so basically, you in this kind of using this approach with conservative theories and realizability, you in fact we don't even need to kind of have this additional complexity of dealing with operators. But rather it's kind of by kind of reasoning in the right theories, we simply can extract, basically reason in some very natural way about things, and then extract the necessary kind of sigma definable proofs from realizability semantics. Yeah. So. Yeah, I think it's all about what I want to tell.
So here working with subset preserving normal planetary functors,
yes,
but you don't need this other condition of the latest, right?
Oh yeah, this is kind of really a point, right? So the latest would be also pullback returning.
Yeah.
But basically, this is too much to demand. So you. Yeah, so I mean, if you would start demand this pullback reservation, then you can start to get problems. Because you cannot build the theory of infinity proofs properly, because it would be very hard to guarantee that the proof. So basically, okay, you would want to have this pullback reservation everywhere in your theory, right? So you would want your infinity proofs to be pullback reserving. You would want then simulations to be pullback and so on. I mean, if it would work, actually, I'm not even sure that even if you would have like pullback reserve proof, probably you still would be able to guarantee the simulation that you're extracting is pullback reserve. So I think it wouldn't help, even if you can guarantee that your infinity proof is pullback reserve. But I think already guaranteeing that the infinity proof is pullback reserve else is not feasible. You cannot actually you cannot do make this kind of guarantees. Yes, so you kind of have to deal with this non-pullback reserve functors. And then we kind of, but the point is actually this gap between pullback reserve function and not, say, if you consider, say, this kind of weakening of the conditional analysis, right, kind of by dropping pullback resolvability, actually the resulting notion is not that drastically different from the latest themselves. So in fact, you can kind of go back and forth between them. that is, if you have yeah, okay. For example, one connection is this. If f is is finitely, yeah, then lambda f of omega plus omega x is a delta. So the one thing, this is basically how you can explain this. Yeah, you could approximate. Yeah, you could kind of basically that's one way of how you extract the latest from finite function. Actually, you could go other way around. So you could kind of think that finite function itself is a term system, but with additional restriction when you can apply terms. And in fact, for the term system to be mapped arbitrary valors to valorders, you can kind of go to a larger function where you drop these conditions on the application of terms, and this you can show that this always will form a later. So really, the kind of the difference between two is not that drastic. So, but sometimes, I mean, of course, sometimes I think basically what's bad about that is this kind of Gerard normal form theorem for that is indeed nice. So basically, you have this easy notion of of denotation system will represent this function as a system of terms, but yeah, I don't think there's kind of laws are that radically different. Actually, they're very much interchangeable. But yeah, but kind of going back to the question, I said, I think kind of the point is that for this particular proof, it was necessary to go through things that are not completely.
All right. Any questions online?
No.
Good. Yeah. If not,
Oh, okay.